Okay, hello, I'm audible to you. Okay, so very good morning to all of you. So we already discussed about the introduction about the conduction, convection, and radiation. And if you have any doubt regarding this, you can ask me. So now we are going to start the second chapter, that is called conduction. Conduction. So first of all, I'm going to talk about conduction rate equation. Rate equation for conduction. And conduction is transfer of energy from the higher energetic molecules of substance to the lower energetic one via interaction, through interaction between the molecules. And mechanism of conduction in the solid is concerned, lattice vibration and flow of electrons. Mechanism of conduction in the fluid is concerned, that is a random molecular motion that involve the molecular diffusion and molecular collision. These already I discussed in the previous lectures. So as far as rate equation is concerned, already I discussed the Fourier's law. But Fourier's law is a phenomenological equation. What do you know by phenomenological equation? Means that is based on the phenomena. There is no any derivation for that. Means it observed from the experiment, from observation. Means observed phenomena. The Fourier's law is phenomenological because it is developed from the observed phenomena rather than being derived. Clear? For example, if you consider a conduction experiment, then let's say what you can observe. How can Fourier's law you can observe? Let us consider a cylindrical rod of a given material. Let's say a cylindrical rod is there of a given material, maybe iron, maybe copper, maybe tin, anyone. So a cylindrical rod is there of a known material or given material is insulated on its lateral surfaces. This is what the cylindrical rod is there. And this cylindrical rod, my dear student, is insulated on lateral. Lateral means chord surfaces. There is insulation is there on the chord surfaces. There is insulation is there. Can you imagine? Means it is wrapped. A cylindrical rod is embedded into the insulation so that no heat can be transferred through lateral surfaces. So if there is a insulation is there on lateral surfaces, lateral means just you can imagine a pen is there and this pen is wrapped with the insulation throughout the lateral surfaces. So if it is wrapped, if the cylindrical rod is wrapped, then only heat transfer is possible through the axial direction. Yes or no? And the end faces, this and this, they are end faces. They are maintained at temperature T1 and T2. They are maintained, means they are isothermal. Isothermal means the left end is T1 and right end is at T2. Clear, beta? We maintain the end surfaces at temperature T1 and T2, and T1 is more than T2. T1 is more than T2. And the temperature difference causes the conduction heat transfer in positive x direction. Yes or no? Let's say this length is delta x and this is what x direction. So since temperature difference is there and they are made of solid, this is rod is there basically. So since it is rod, then obviously heat transfer through conduction will take place, and if temperature difference is there, that causes the conduction heat transfer in the solid. Yes or no? So what the Fourier has observed, that's why the Fourier's law is phenomenological equation. If let's say T1 and T2, if temperature drop remains constant and if delta x is constant, if temperature drop is constant, T1 minus T2 is constant, and length of the rod is also constant. If we increase if we varying the area, area and direction of heat transfer. I told you area is normal to direction of heat transfer. So this is area I am talking about. This is area normal to direction of heat transfer. This is area normal direction of heat transfer. Okay, beta. Heat is transferring from the left to right because T1 is more than T2. Clear? And area is normal to direction of heat transfer, and area is not function of x because area is constant throughout. Yes or no? Normal area is constant throughout the length. So what the Fourier has observed, if temperature drop, if delta T, which is T1 minus T2, here I will discuss delta T as a high minus low temperature, is constant, delta X is constant, then on varying the area, rate of heat transfer get vary. And what we found, when he increased the area by twice, then rate of heat transfer become twice. From this observation, what he observed, the rate of heat transfer is proportional to area. Yes or no? So if delta T is constant, delta X is constant, then the rate of heat transfer proportional to area. Second, if area and delta T is constant, Q proportional to 1 upon delta X, inversely proportional to length, direction of heat transfer. And third, area and delta X is constant, Q dot proportional to delta T. Clear? Temperature difference. So finally, if we observe, this is for given material. So for given material, the rate of heat transfer proportional to what? A into delta T upon delta X. Any problem with that? And listen, if this all three are same, let's say area is same, delta X is same, and delta T is same, but if the material is changed, then again the rate of heat transfer is going to change. It means it's also depend upon the material property, and that property is called thermal conductivity, and hence the Q is equal to, here I should write Ka into delta T upon delta X. Clear? So here delta T is basically T1 minus T2. That's why I minus and I have not written here. Clear, beta? And if this delta X tends to 0, in that case the Q dot is equal to minus Ka into dt upon dx. Is this clear? Now here dt is final minus initial. This is what the Fourier's law. That's why there is no derivation for the Fourier's law. It is just a phenomenological equation. And this is what the heat transfer in x direction means. Q dot x, qx. And as far as flux is concerned, small qx is equal to minus k into dt upon dx. Is this clear, beta? And this minus sign indicates temperature get decreases in the increasing x direction. This is what the Fourier's law. And from this observation, what we found, ki heat transfer is a directional quantity. Yes or no? It is a heat flux or rate of heat transfer is a directional quantity. And direction of qx is what? Normal to. It is a directional quantity, a vector quantity, and its direction is sir, if I have written dx, this dt upon dx, if you integrate then you should integrate, sir, Mr. Prajot. Sir, delta x is not for dx, is for small length, and if the requirement is, you can integrate. I already integrate one equation in the last lecture. You should revise the lecture, then you should ask the question, Mr. Prajot. This is what for small dx. If you integrate this equation, you will get the same equation here. Chavi, in the last lecture, had I integrated this equation, yes or no? If delta x is not function of, if q heat flux is not function of x, sir, Mr. Prajot, qx is equal to minus ka into dt upon dx. That I had written last lecture. If area is not function of x, then q dot x into dx is equal to minus ka in dt. Area is not function of x, then you should write separately. Now when x equal to 0, when x equal to, you can write x1, temperature is T1. At x equal to x2, temperature is T2. Then q dot x into x2 minus x1 is equal to minus k into a into T1 minus T2. This is plus sign. Then q dot x is equal to, here k a into delta t upon delta x, that I have written in the last revise the lecture. But this equation you can't use if the area is function of x. Can you write this? Can you write q equal to ka? Let's say, sir, okay sir, so you can write, but why you are not revising the lecture? If the same rod is there, if the same rod and its area is going to vary like this, and again lateral surfaces are insulated, this is what x direction, it's x1, it's x2. Now tell me, can you write this equation as a heat transfer q dot x is equal to, this is q dot x, can you write, if this is a t1, this is a t2, can you write this equation as a t1 minus t2 into k upon delta x? Can you write into area? Is the area is constant? Is the area normal direction of heat transfer? This is the area. If you see here, area is different, at this point area is different, at this point area is different. Area is a function of x in this equation. So you can't write, sir, that's why I can write only the Fourier's law as a q dot x is equal to minus k a x into dt upon dx, only over the small differential element when dx is very small, dx, and here drop is dt, only over the smaller element where dx tends to 0, in that differential area only I can write the q equal to minus k dt by dx. Okay sir. So first of all, I was talking about the rate of heat transfer is directional quantity, and it is its direction is normal to cross sectional area. Yes or no? Normal to cross sectional area. So what we found, heat flux or rate of heat transfer is a vector quantity. Yes or no? Heat flux or rate of heat transfer is a vector quantity. So in Cartesian coordinate, we can write the, in Cartesian coordinate, my dear student, how I can write the, if this is any isothermal surface is there, is there any, if this is any isothermal surface is there, and this is what the normal to this, it's normal to this, then here normal to this, there is a qx, this is what qn, am I right? Qn, what qn? Normal to direction of heat transfer. Then here it's qx component and this is qy component. Yes or no? Qx, qy. Qn is nothing, it's a rate of heat transfer of heat flux in normal direction. Yes or no? And this is normal to isotherm. This is what isotherm. Isotherm means isothermal surface is there. So basically what I'm saying to you, this q called as heat flux, I can write as a qx into I cap, qy into j cap, plus qz into k cap. Yes or no? Because heat is a vector quantity, this is what the normal direction, this is x, this is y, and again z is there that I can't show here, but this is the heat flux which is a vector quantity. Bolo clear hai? Where qx I can write as a what? Minus k into dt upon dx. Qy I can write as a minus k. Here also you can write kx and ky. I will discuss dt upon del t upon del y, and qz equal to minus kz into del t upon del z. They are partial derivative because temperature is function of more than one variable. ठीक है? So in short we can write q as a qx minus k x into del t upon del x. Flux I am going to write here minus ky into del t upon del y plus minus kz into del t upon del z. Now into I into j into k. Please write I j k. I j k please write I j k. ठीक है, ये x component, y component, z component, and this contributes to total heat transfer q bar. Q bar vector quantity. Heat flux is a vector quantity in x, in y, in z, and if you want to find magnitude, then under root qx square, qy square and qz square, that you know very well. Okay beta, if kx is equal to ky equal to kz equal to k, what if y, I will discuss what is kx, ky, kz, it's k, then also you can write here minus k, I can take common, and this is gradient of T temperature, yes or no? Because you know gradient of any scalar is a vector quantity, minus k. This is what the Fourier's law of heat conduction in general, and you must know this Fourier's law is valid for solids, liquid or gases, or for all three. So this is what when temperature is a function of x, y and z. Okay, what is one dimensional heat transfer? This is the three dimensional. What is one dimensional heat transfer? For example, let's say if you are going to consider heat transfer through wall. In a room, your wall is there, na? In your room, there is a wall. The room inside you are studying, it's surrounded by the wall. Let's say I'm going to consider one wall, your left side wall, and this is the left side wall. ठीक है बेटा? Now in this left side wall, if you see, there's three coordinates there. This coordinate, and another is this coordinate that is here. So it's x, it's y, let's say it's z axis. Three axis is there, yes or no? Now, if this axis is mean delta x, if delta x is small compared to delta, so first of all what I am assume कि left surface, ये जो left surface है, this is maintained at a constant temperature. Left surface is maintained at a constant temperature, है ना? And so delta x, this is what delta y, and this is what delta z. Temperature may vary in the x, y and z, but what during Fourier's law, what I assumed here कि this Fourier's law is applicable for minus k a dt upon dx, means there should be a plane where temperature should be constant. Now at this plane, here temperature is T1, here is T2, here is T3, here is T4. So temperature is varying along this direction, but at any plane temperature is constant throughout. That is assumption is there. That's why I have taken the isothermal surface. Are you getting a point? And listen, temperature variation in the y and z is negligible. Why? Because the length in y and z is very long as compared to x. Temperature variation in y direction and z direction is very, it's called as one dimensional heat conduction. Why one dimensional, my dear student? Because temperature variation in y and z, because length of the y and z is very large as compared to x. A thickness in x direction is very small as compared to y and z direction. That's why if any variation is there, that variation is only found in the x. Is this clear? Any variation in the y and z is very small, that can be ignored. Clear beta? So by ignoring, we can simplify our problem as a one dimensional heat conduction. Otherwise what happen? What is two dimensional? As far as two dimensional is concerned, where temperature is going to vary with x and also temperature is going to vary with the y. This is two dimensional heat transfer, yes or no? So in our syllabus we have to only cover the one dimensional heat conduction. In our syllabus we have to only, so how I can make it two dimensional, one dimensional? By considering the variation in the y and z is very small, or it can be neglected. Only we should bother about temperature variation in x, because thickness of the wall in x direction is very small as compared to rest two direction. Okay? So this is how I can simplify our problem from three dimensional to two dimensional and two dimensional to one dimensional. Now here I kx, ky, kz. Actually, my dear student, there are this is what thermal conductivity. I told you thermal conductivity is the ability of the material, or it simply indicates you the ability of material to conduct the heat. Yes or no? I told you in the last lecture. Yes or no? Thermal conductivity is nothing. It's simply ability of material to conduct the heat. Every material have different capability, different ability to transfer the heat. So that's why we should use one property, and that property name is called as thermal conductivity. This is the physical significance. But what is definition? Thermal conductivity rate of heat transfer. Thermal conductivity is equal to rate of heat transfer through a material of unit thickness, unit area and unit temperature drop. Yes or no? K is equal to Q. K is equal to Q if area is unity, delta T is unity and delta X is unity. Yes or no? Or you can say thermal, if material thermal conductivity is given as, if thermal conductivity is given as 45 watt per meter per Kelvin, it means that material, if material is subjected to unit temperature drop of unit thickness of unit area, then the rate of heat transfer equal to thermal conductivity of the material. ठीक है बेटा? तो material may be isotropic and anisotropic. What is isotropic material? So there are few materials are there whose properties are going to vary with direction. Means in x direction, in y direction, z direction, their property of their ability to conduct the heat may be different. It is clear? For example, let's say this is what the material I have drawn here. So in x direction, the ability is conduct the heat is different. In y direction, the ability of material is different. In z direction, the ability of material to conduct the heat is different. That's why kx, ky and kz. In the same material, the ability of the material to conduct the heat, this is called as thermal conductivity, may vary, and that types of material is called as anisotropic material. That types of material is called as anisotropic material. ठीक है बेटा? तो but in general most of the material is isotropic. Isotropic means whose properties or whose properties of the materials are independent of direction. That is called as isotropic material. ठीक है बेटा? Isotropic. So this is basically for isotropic material. What is isotropic material? The material whose properties, not any thermal conductivity, any properties, whose properties are independent of direction. Isotropic material. So here I am talking about property as thermal conductivity. So for isotropic material, the thermal conductivity of the material will not vary with direction. In all direction it will be equal. And I told you, out of thermal conductivity of the solids, liquid and gases, which is highest. So in the solid, thermal conductivity is larger than the liquid, and in liquid larger than the gases. Yes or no? And in the solids, solid may comprise of free electrons. Again listen, solid may consist of free electrons and atoms bound in the periodic arrangements called a lattice. Yes or no? So I told you already, but I am going to discuss here. So in modern view of material, the solid may be comprised of free electrons and atoms bound in the periodic arrangements, that is called lattice. So there is a free electrons and lattice. Lattice means periodic arrangements of atoms or molecules. And according to transport of the thermal energy, the thermal energy may transport due to following two effects. One is migration of or translational motion or migration of free electrons and the lattice vibration waves. Did I told you? In pure metals, you know, contribution due to electron, free electrons to conduction heat transfer is dominant as compared to lattice vibrations wave, that is phonons. The wave, lattice vibration wave is also called as phonons. Clear beta? So in the pure metals, if I am talking about, which will dominate, obviously the conduction heat transfer through flow of free electron will more dominate over the phonons or lattice vibrational waves. Whereas in non-conductors and semiconductors, which will dominate? In non-conductors and semiconductors, which phenomena will dominate? Lattice vibrational wave or flow of electrons. Conduction due to which mode will dominate? Lattice vibration, also called as phonon. ठीक है? Okay, well, this is things already we discussed. Now come to the next that I am going to discuss here is thermal diffusivity. There is a property called as thermal diffusivity. Acha, one more thing. Do you know thermal conductivity of alloys are much lower than the thermal conductivity of pure metals? Yeah, mixture of more than one metal. When two or more metals are doped together, that's called as alloys. Tell me any name of alloy and their constituents. Tin is alloy. Alloy of what? Brass is alloy of copper and zinc. Yes. Iron, cobalt, nickel. Very good. Let's say I'm talking about brass. Brass is alloy of copper and zinc. What is bronze? Bronze is also alloy, na? Copper and zinc. Okay, for example, let's say what I'm telling. Let's say I'm saying here C. C is the alloy, and this is constituents of the species A and B, pure metals. A and B are pure metals, and when they are combined, then it becomes C. C is alloy. So what happened? The thermal conductivity of the alloy is much lower than the thermal conductivity of the A and B. Means it is low. Thermal conductivity of the alloy is lower than the thermal conductivity of either of the pure constituent species. Clear, beta? Why it's so? Because when we are going to, let's say this is thermal conductivity, let's say 50, and here it's 30. When I just, it's watt per meter per, it's thermal conductivity. When I mix it together in some proportions to make the alloy, then its thermal conductivity is less than 30. It's 20 is here, less than either of the material. Why it is so? Because when we are going to dope foreign atom into the pure element, pure metals, let's say B is a foreign atom. When we are going to dope this A with the B, then it will strongly influence the flow of electrons. Okay guys, clear hai beta? Batao. When we are going to add the any foreign molecules into the other, that will strongly hinder the effect of, strongly suppress the flow of electrons. That's why the thermal conductivity of the alloying material is lower than the either of the pure constituent species from which it is made of. Okay, that you should keep in mind. Clear? Now, listen, in the study of heat transfer problem, several properties of the matter has been used or will be used, and these properties are generally referred to as a thermophysical properties. So what is thermophysical properties? Means in the study of heat transfer, we will go through the different properties, and that properties are generally referred as thermophysical properties. And thermophysical properties include the two distinct categories. One is transport properties and another is called as thermodynamic properties. Clear beta? Transport properties includes the diffusion rate. What is transport properties? The transport properties include the diffusion rate coefficient, which measures how fast the diffusion will take place. Similarly, in the momentum transfer, it's a kinematic viscosity, momentum diffusivity, for the momentum transfer. Similarly, in the heat transfer, there is thermal diffusivity. Are we getting point? So these are transport properties. I told you na, whatever disturbance has been taken place on the surface, that will propagate in the rest of the fluid by the momentum diffusivity. Similarly, if any thermal disturbance will taken place on the surface, that will propagate in the rest of the fluid by the property thermal diffusivity. Clear? So just like momentum diffusivity, there is thermal diffusivity. They are transport properties, means which are used as a transport of the energy, mass and momentum. As far as energy is concerned, it's thermal diffusivity. Mass is concerned, it's mass diffusivity. Momentum is concerned, it's momentum diffusivity. Clear? So first of all, we must know in study of heat transfer, we will go through the thermophysical properties, and these thermophysical properties can be categorized in two parts. One is transport properties and thermodynamic properties. Transport properties is concerned, that is the diffusion rate coefficient. Okay? Such as thermal conductivity for the heat transfer. Now come to the picture here. I am talking about the one property, that is rho and Cp. What is rho Cp? Density into Cp when they are in the product. So you know mCp is what? What is Cp first? You must know Cp is the specific heat capacity. Its specific heat capacity, and its meaning is only कि amount of heat required, amount of energy supplied, amount of heat supplied to raise the temperature of unit mass of substance by unit degree Celsius. Yes or no? I told you in the process calculation. कि if you have a unit mass of substance, if Cp is given as 10, what does it means? It means the 10 unit of heat has to be supplied to raise the mass of unit kg of substance, unit mass of substance by unit degree Celsius. In order to raise the unit degree Celsius temperature of unit mass of substance, 10 unit of heat must be supplied. That's what meaning is that specific heat capacity. So if m kg substance is there, then how much heat should be supplied? mCp. And if we divide mCp by volume, that become density. So this is called a volumetric heat capacity, yes or no? Specific means per unit mass. Clear beta? Specific heat capacity means per unit mass. If I multiply with this, what is mCp? What is mCp? It's simply called as heat capacity, because it's not a specific. Specific means per unit mass. It's simply heat capacity, and sometimes we call it also called a heat capacity. This is clear. And if I divide by mCp by volume, this is called as rho Cp, and this is called a volumetric heat capacity. It's a heat capacity per unit volume. This is volumetric heat capacity. Volumetric heat capacity. Clear beta? Volumetric heat capacity, rho Cp. So when I multiply two thermophysical properties, density and specific heat capacity, that become volumetric heat capacity. And what does it measures? When it's multiplied combinedly, rho Cp, it's measure the ability of material to store the thermal energy. Because rho Cp is storing capacity, how much energy get stored has to be absorbed in order to raise the temperature by unit mass. More the Cp, more the heat should be stored. Yes or no? So it is simply, it is a measure of, it measures the ability of a material to store the thermal energy. Store the thermal energy. ठीक है? तो rho Cp is the property of material which measures the ability of the material to store the thermal energy. Clear? And you must know, a substance of large density, substance having large density, are typically characterized by smaller specific heats. So one ability is called as rho Cp. And what about K? K is the ability of material to, K is ability of material to conduct the heat. Yes or no? K is the ability of material to conduct the heat, my dear student. So there is a very important property, that is thermal diffusivity, which is the ratio of, it is alpha, which is ratio of thermal conductivity to the heat capacity, conductivity to the volumetric heat capacity. This is called as very important thermal diffusivity, and this is K upon rho Cp. So it's a very important property in the study of heat transfer medicine, and this unit is meter square per second. You can check K by rho Cp. And what does it measures? Anyone? It is a measure of ability of material to conduct the heat with respect to ability to store the thermal energy, because every material have two property. One is ability to store the heat and ability to conduct the heat. Then we have to talk about, now you can't say, for example, if a material having K is higher, let's say K is 10 and other material is K is of 20, then you can't say this material have more ability to conduct the heat as compared to this by only seeing the K, because along with the transporting properties, there is one more property called as storing capacity, because whatever energy has been entered here, although it may transport, but it may also have more storage capacity. Are we getting a point? Yes or no? So ability of material to conduct the heat cannot be only decided by the thermal conductivity, because material has two property. Material has one more property, is called storing capacity. It can also store more. Yes or no? Clear? Let's, for example, here K is 10 and here K is 20, and here rho Cp is given as let's say 5, and here rho Cp is given as let's say 15. Then although for this material K is less as compared to the second material, yes or no? Here K is 10, here K is 20. Now in the first instant it seems to be that the second material will have high ability to conduct the heat, na? Or rate of heat transfer should be faster in the second. But I told you every material have two property. One is transport property, ability to conduct the heat and ability to store the heat. But if you see, the storing capacity will also play important role. The storing capacity is more for the second material. Then if you write the thermal diffusion K by rho Cp, then 20 upon 15, and this is what 10 by 5. It's 2 here and it's less than 2 here. So what you found, the second material will diffuse the heat with a slower rate as compared to the first material, although the thermal conductivity is more for the second material. Is this clear? Now K will play important role only when, let's say, any heat is stored. Then how stored heat can be propagate faster in the material second. But if I am talking about transfer of the heat, diffusion, rate of heat diffusion, so rate of heat diffusion is faster in the first, in this case. Clear, beta? Or you can say thermal diffusivity is a ability of the material to conduct the thermal energy with respect to ability to store the thermal energy. It means material of large thermal diffusivity, listen, materials of large alpha will respond quickly to change in their thermal environment. Yes or no? Just like you might have seen, you might have studied the in the process control, the time constant. Lower the time constant, faster will be the response. The material which have any system which have low time constant, lower time constant is a measure of speed of response. Lower the time constant, faster will be response. Similarly here, the material which have high thermal diffusivity will be more sensitive for any change in the environment. That's meaning of, this is the meaning of thermal diffusivity in the sense of sensitiveness. If any small change will be happen in their environment, they will respond quickly for that. Is this clear? So materials of large alpha will respond quickly to change in their thermal environmental disturbance, whereas material of a small alpha will respond more sluggishly and taking longer to reach the new equilibrium condition. It means diffusion, or you can say rate of heat transfer, slow and fast. It means how fast the heat will get propagate to the material, that will decide. So please write, thermal diffusivity is measure of ability of material to conduct the thermal energy with respect to ability to store the thermal energy. Please write down. It measures the ability of material to conduct the thermal energy relative to its ability to store thermal energy. ठीक है बेटा? Materials of large alpha will respond quickly. Will respond quickly means it will reach faster to the new equilibrium state. Means suppose if any material is there, two material I have, one have alpha equal to let's say 20 meter square per second, and here alpha is 30 meter square per second. ठीक है बेटा. Then and they both are the same temperature of 100 degrees Celsius, 100 degrees Celsius, and when they placed in the environment of 10 degrees Celsius environment temperature, then which will reach the first environmental temperature, which will cool to the first equilibrium to the surrounding. Below, which will reach first. Initially their temperature is same, ना, the only the and environmental conditions are also same. ठीक है बेटा. So which material will cool first, or which material will heat first? I'm talking about respond. So here this material will get cool. Which material will cool first? The material which have high value of alpha. You should not decide by K, you should decide by alpha. ठीक है. It means the material of large alpha will respond quickly. No. Yes. 30. The materials of large alpha will respond quickly to changes in their thermal environment. In their thermal environment. If any small change is there in thermal environment, that will quickly sensed by the material having large value of alpha environment. Clear beta? Whereas material of small alpha will respond more sluggishly. And taking longer to reach new equilibrium condition. ठीक है. It's just similar to the time constant. ठीक है बेटा. For example, another example, let's say this is the two material is there of the same surface area and same, everything is same. Now here initial temperature is 100, and this is exposed in the environment of 200 degrees Celsius. Which will heat first? Its alpha is 20, here alpha is 30. Which material will heat first? Heat means which material will lead to the new thermal, because obviously that heat will transfer and this will lead to the 200 degrees Celsius. It will get heated. Again the material which have high value of alpha, second material. So if second material will heat first and cool first, or it will lead to the new equilibrium state faster having high value of alpha. ठीक है. Quick response is there for any change in the thermal environment. This is alpha K by rho Cp. Clear beta? Thermal diffusivity. Now one question you can write, please. The thermal diffusivity, and one more thing, thermal diffusivity is a controlling transport property for transient conduction problem. Transient means unsteady state, because time will come into picture na. That's why you used to write very important point. This thermal diffusivity is the property of a material or transfer property for transient conduction. Transient means, why transient? Where time come into picture, unsteady state conduction. Listen, it is our question for aluminum at 300 Kelvin, density Cp and K is given as 2702 kg per meter cube. Cp is 903 joule per kg per Kelvin. K is 237 watt per meter per Kelvin. ठीक है बेटा. At 700 Kelvin for aluminum only. Aluminum at 700 Kelvin density Cp and K are given as 2702 kg per meter cube, 1090 joule per kg per Kelvin, and this is 225 joule per kg per Kelvin. If you see, I told you, as far as thermal conductivity of the solid is concerned, when temperature increases the K should be increased, but I told you one exception is the aluminium, है कि नहीं? So you can see even the aluminium is sorry, aluminium is a metal, then obviously it get decreases. Okay, as temperature more hindrance is there. Aluminium is exception, but up to some certain temperature range, not for all temperature range. ठीक है? Now this is so what is alpha in this case? What is alpha in this case? What is thermal diffusivity at 300 Kelvin and 700 Kelvin? Can you tell me? So this is how I can calculate the thermal diffusivity. If you solve this, found to be 97.1 into 10 power minus of 6 meter square per second, and this is found to be 76 into 10 power minus of 6 meter square per second. So obviously it seems to be aluminium is more sensitive for any thermal disturbance at the low temperature as compared to high temperature, na? Okay, one more thing I would have discussed here. Now write the heading is general heat conduction equation in Cartesian coordinate. Heading is general heat conduction equation in Cartesian coordinate system. General heat conduction equation. The first I'm talking about in Cartesian coordinate system. Cartesian means rectangular coordinate. Rectangular coordinate system. So in rectangular coordinate system, temperature is a function of what? X, Y, Z and time? Yes or no? In Cartesian coordinate system, temperature is a function of X, Y, Z and time. Is this clear? So we have to write the general heat conduction equation for the Cartesian coordinate. So my dear student, what I am going to consider here, let's say this is my what axis is there, and this is my axis is here X, this is what Z and this is what Y. ठीक है? Clear beta? So if this is, then this become what? Delta X or dx you can say. So in we have considered small differential element in a Cartesian coordinate system. This is small differential element that I am going to show you in large way, but actually it is very small. This is very small. In the larger system there is, you can think in this way. This is the larger system was there. In larger system what I consider, I just consider small differential element, and that I exaggerate here. Is this clear? Because we should only work on the differential element, because temperature may vary, that's why we have to assume small differential element that I have exaggerate here in larger form. So this length is dx, and why we have assumed small differential element? Because in that element temperature is a function of X, Y, Z and time. That's why we have to consider when temperature is going to vary in X, Y, Z, we should assume a small differential element in X, Y, Z as well, है in all three direction. If it is only going to vary with X, then we should assume the differential element only in X direction. Yes or no? But here since temperature is going to vary in X, Y and Z, that's why we should assume a small differential element in X in dx, Y in dy and dz in Z direction. Yes or no? So this is what dx, this is what dz and this is what dy. Clear? And over this element I will just consider, I will apply the rate of heat transfer by conduction. So my dear student, here it's simply q dot x, heat transfer in x direction. This is x direction, yes or no? Bolo. Q dot x, heat get in, then here through this heat get out, बोलो. This to be written as q dot at x plus dx. Also you can write as a this. You can write first, है ना. कोई any problem. Also here heat enter in this is qz and heat getting out is qz plus dz. It's a flux. Same thing is in the y direction. As far as y direction is concerned, it's q dot y and here out should be q dot y plus dy. ठीक है बेटा. Then if you write the energy balance in the system, what the energy balance is there? Energy get in minus energy get out. Energy can be generated na. Below energy can neither be created cannot be destroyed, but there should be some heat source may be there. So how can I write the energy balance in this case? It's simply E dot in minus E dot out, and if there is any heat source is there, then energy can generate. E dot generation is equal to E dot accumulation. This is what there is. This generation is just because of heat source. This is the energy balance. Any problem in this case? If sink is there, then minus will be there. But here I am going to write generation term. Means there must be energy source. So one by one I am going to discuss. कोई problem यहाँ तक? Now there must be some energy source. So here E generation is there, and also there is a heat stored. Energy get stored in this system only. So how can find the energy generation? E dot generation is the uniform heat source. There will be heat source is there, and that heat source providing the generating the energy as a uniform heat generation per unit volume. So if let's say Qg, what is Qg dot? Qg is the volumetric heat generation. Listen, Qg is the volumetric heat generation. It means it's watt per meter cube. Means in unit volume how much heat gets generated, the heat source. There is a heat source within the material, and that heat source, this may be a nuclear source, है ना. So this heat source may generate the energy in terms of unit volume. So per unit volume of this material is made of, let's say I am talking about this material made of nuclear source, then obviously it will generate the heat as well. So Qg is watt per meter cube. The unit volume में how much heat will generate Qg, then total volume is how much. If you multiply with the volume, this is dx into dy into dz. This is what the meter cube. So it's watt. The rate of heat generation is Qg into dx dy dz. Yes or no? This is what Qg dot into dx into dy into dz. This is what the total heat generation. So listen, the Qg is the volumetric heat generation, where Qg is volumetric heat generation. Volumetric heat generation. Volumetric per unit volume. There will be some heat generation per unit mass may be also there. If per unit mass is there, then what should I do? If let's say the heat generation is given as a per unit mass, then how can I find the Eg in that case? If Qg is not given, if they've given the heat generation per unit mass is given, mass of substance is given, then how can I find the Eg? So again Qg into mass, and mass is volume and density, then density will come into picture. ठीक है बेटा, clear? तो you should be very careful कि is this Qg or it this Qm. Qm is the mass heat generation per unit mass, and Qg is the volumetric generation per unit volume. That you must be clear from the units. Is this volumetric or it's mass? Is this clear? Now what is energy stored here? E dot stored. Energy stored is simply accumulation. Energy can be stored in only in form of internal energy. Yes or no? This is what d of u upon dt. It's a internal energy, rate of change of internal energy that is stored in the system. I told you the energy in the very first lecture. Energy is stored form. Energy stored form may be macro and micro. So basically, it's a sum of macro plus micro. Energy is stored in form of micro plus energy is stored in form of macro. Please, you can check the notes. Energy can be stored in two forms, microscopic and macroscopic form. Of microscopic form of stored energy is called as internal energy, and the macroscopic form of energy is due to kinetic and potential energy of system due to its translation and its position. So basically, this is what d upon dt, or not d here, del should be there. Why? Because del t, del upon del t, and energy stored is here basically internal energy plus microscopic form of energy is kinetic energy and ek plus ep, potential energy. My dear student, since system is stationary, it is not moving anywhere, is there any change in kinetic energy? So del is change, the change in kinetic energy is negligible. System is not elevating any position, है ना? तो system is neither moving or it's moving with, if moving then it's moving with the constant velocity, then change in the kinetic energy is zero, and system is fixed at position, that's why the change in the potential energy is zero. Then stored energy may only part will rest is del u upon del t. Is this clear? And u is what? It's internal energy of system. And also I told you that in the case of solids and liquids, internal energy Cp is either Cp or Cv, whatever you connect, they are equal. No? For incompressible substances, Cp and Cv are equal. I told you? Yes or no? Cp and Cv are only meaning for the gases, but for incompressible substances there is no meaning. Otherwise value is only mCv dt. Clear beta? I told you du equal to mCv dt. So in general you should write here del u is a del u, this should be m cv. So what is mass, volume and density? So it's rho, volume is dx and dy dz, this is mass, into cv into t, this is temperature upon del t. And since density and volume and cv, they are not going to change with the time. Temperature may change with the time, but these properties are not changing with the time, that's why I can take it outside, and that ultimately become rho cv into dx dy dz into del t upon del t. Clear beta? This is what called as accumulation term. And basically cv and cp are equal, that's why I can also write cp as well, no issue, because since cp is equal to cv for incompressible substances, then I also rho cp into dx dy dz into del t upon del t. Because why these are going to outside? Because they are not going to vary with the time. कोई problem बेटा? So we define the generation and store term. If you see the very starting lecture, I told you that energy can be two form. Energy in transit, energy in stored. Energy in stored has two form, macro and micro. Macroscopic form of energy is due to internal energy, and the rest two is due to macroscopic form of stored energy. Macroscopic means when the system is moving or it's at some position from the reference level. So since although their potential energy is there, although the kinetic energy, but change in the potential, change in the kinetic energy is zero. Change is zero. Change in the potential and change in the kinetic energy is zero. I'm not talking about potential energy is zero. Potential energy is there, but change in the potential is zero because the system is not elevating any position. Is for a stationary system, it means in short you can say for a stationary system that change is zero. The only internal energy will be changed here. Now energy is going to be in here. Energy is going to in by a conduction, convection, radiation. Tell me please. Now energy is going to in only through conduction because I am adding a conduction equation. The energy getting in through conduction, energy get out through conduction, through all direction. So energy get in through conduction is qx plus qy plus qz. Now E dot in is equal to q dot x plus q dot y plus q dot z. E dot out is q dot x plus dx. q dot y plus dy, q dot z plus dz. Yes or no? Since q dot x plus dx, my dear, is nothing, it's simply from Taylor series, it's simply q dot x plus del q dot x upon del x into dx. That I told you already, because if you recall, sometimes I am writing the same question as this, q dot x, then here q dot x plus del q dot x upon del x into dx, means how much change is there. Here it's q dot x, just like I told you in the fluid mechanics, u here, then here u plus del u upon del y into dy. Same thing you can also write here, u at x, then u at y, then u at y plus dy. So y plus dy is nothing, it's simply from Taylor series expansion that I got here. Is this clear? Similarly, q dot and y plus dy is nothing, q dot at y plus change in q dot at y with respect to y into distance of dy. Q dot z plus dz is q dot at z plus del q dot z upon del z into dz. This is what here. If you put all equations into the main equation of energy balance first, please put. Then if you put this equation, then q dot x minus q dot x plus dx is what? Please simplify. Only you have to simplify. If you put in this equation, then E dot in minus E dot out is nothing, it's minus del q dot x upon del x into dx plus del q dot y over del y into dy plus del q dot del upon del z into dz plus qg dot into dx dy dz is equal to rho into dx dy dz into del u upon del t. Is this clear? Sorry, into cv or cp into del t upon del t. Is this clear? This is what equation I got by putting this in. And this is since from Fourier's law, what is q dot x minus k, and I'm talking about isotropic material, so minus, then kx will not be there, minus k into dt upon dx, it's flux. I'm sorry for that, this should be capital Q, because it's the rate of heat transfer now. Capital Q, everything is capital Q. This is small qg, no issue, because it's per volume, but the rest are the capital, rest are capital, because I'm talking about rate, rate proportional to area as well, not flux. This is small qg. Now since from the Fourier's law, what is q dot x minus k into what area should be? Area normal direction of heat transfer? Tell me. What is the area in x direction? Tell me from this figure, what is area normal direction of heat transfer? What is area normal to direction of heat transfer? Mr. Prajot. dy dz, yes. So into dy into dz into del t upon what? Del x. What is q dot y? Minus k into dx dz into del t upon del y. What is q dot z? Minus k into dx dy into del t upon del z. That is what here. And if I put in this equation, then I got here minus, I take common, del upon del x. Listen carefully, Deepika, del upon del x. I am just putting the value of q. So what is q? It's minus k into dy into dz into del t upon del x and bracket close, and outside this is dx. Clear? And these all terms are inside the differentiation. Similarly, plus del upon del y minus k into dx dz into del t upon del y bracket close into dy plus del upon del z minus k into dx dy into del t upon del z into dz. Yes or no? Bracket close plus qg dot into dx into dy into dz is equal to rho dx dy dz cp into del t upon del t. कोई प्रॉब्लम बेटा? सिंपल है, वेरी सिंपल. सुनो निधि, कूलर एसी बंद कर दो, ये चला दो. इसके लिए ये बचा दो, हमको ये फाइनल चला दो बस. Now what is now here I am going to write very important thing. Can you take this dy dz outside this differentiation? Tell me, can you take this dx dz outside this differentiation, because these all terms are inside the differentiation here. That you can take this dy dz is actually area in normal direction of heat transfer, the area normal to x, and this you can take it outside only when the area is not function of x. This dy dz you can take outside the differentiation only if this area is not function of x. This dx dz you can only take outside this differentiation when it is not function of y, and this dx dy is the area normal direction of z direction, and this you can take only outside when it's not function of z. Yes or no? And in this example, in this figure, you can see the area normal to direction of any coordinate that is constant. It's not going to vary. Yes or no? Is the area is going to vary? For example, if I'm talking about this area, if I'm talking about area in x direction, then either at this or at this or at this, at all three area normal direction of x is only dy dz. Yes or no? Similarly, in z direction, area is always dx dy. It's again constant. So in this example, I can take it outside. So now, my dear student, from this equation, if I take the area outside, then whatever resulting equation that I will get, that resulting equation has now one limitation. What limitation is there? Okay, that can be only used for constant area, where area must be uniform. Clear? If I am taking these terms outside the differentiation, that it means the resulting equation is valid for only uniform area. Yes. Clear? You can't use these equations for the geometry where area is going to vary. So whatever simplified equation that I will get here, that can be only valid for uniform area. That you must know. So you can write in your languages. Okay, this, since area is constant, that's why I can take it outside. Then if you take it outside, then what the resulting equation I get here? Now minus minus become plus, or minus you can take common, this become plus. Okay, and this become what? And let's say k. Now again, one more simplification. One now I will not make simplification for k here. So then plus, and this become del upon del x into k into del t upon del x. This is the first equation. Del upon del y into K into del T upon del Y plus del upon del Z into K into del T upon del Z plus into dx dy dz. I will just take outside here in every terms there is dx dy dz will come out, and I will divide by dx dy dz whole terms, then cancel out here, and यहाँ पे सब कुछ cancel हो जाएगा. Then only here qg is there is equal to rho cp into del t upon del t. Clear? Now can I take k as a outside, because here k, here k, here k. Can I take k outside? No, even for the isotropic material, I can't k outside, because k may be function of temperature. If k is a function of temperature, then obviously k is also function of x. Because as in general, k is a function of temperature, and temperature in function of x, then indirectly k is a function of x. No. I have already assumed kx, ky, kz are same. But what I'm talking about, k may be function of temperature, yes or no? K is a function of temperature in general, we have already seen, and temperature is function of x, because temperature is function of x, y and z. X, y and z. Yes or no? Then this k I can't take outside if k is a function of temperature. Is this clear, beta? Because this is the definition of x here, and this k may be function of x, because k is a function of temperature. Is this clear? So this k I can take only outside if k is not function of temperature. Is this clear? So if k is not function of temperature, then I can take it outside. Otherwise, this is what general equation is there. Otherwise, this is your general equation. Is this clear? Then I can take it out k into del 2t upon del x square, del 2t upon del y square, plus del 2t upon del z square, plus qg dot is equal to rho cp into del t upon del t. And if we divide the whole equation by k, then this is what del square t upon del s square, del square t upon del y square, del square t upon del z square, plus qg dot upon k, and here 1 by alpha into del t upon del t. Yes or no? Please check. Alpha is k by rho cp, then rho cp upon k is 1 by alpha, and this we can write as a Laplace function del square t. Yes or no? Plus qg dot upon k is equal to 1 upon alpha into del t upon del t. This is what the general heat conduction equation. It's general but with two assumptions. What two assumptions are there? Although it's not general तो ये है. This is what you general. इसके पहले वाला जो इक्वेशन था. One assumption is it's for 3-dimensional and uniform area, and k is not function. This two is a very important assumption is there in this equation if you want to write. So whenever you will write this equation, whenever you want to use this equation, you should be very attentive that there is two assumptions I have considered. That is what uniform area and k is not function of temperature. Then only you can use this equation, and Cartesian coordinate system obviously. Okay. Okay, can you tell me what is the equation for if I'm saying write general heat conduction equation for one dimensional heat conduction थ्रू अ प्लेन वॉल. प्लेन वॉल क्या है? सिलेंडर है, रेक्टेंगुलर कार्टेशियन कोऑर्डिनेट है. वन डायमेंशनल हीट कंडक्शन थ्रू प्लेन वॉल with k as a function of temperature. Tell me. Write the expression for this. How will you write from general? So write is general heat conduction, one dimensional heat conduction. One dimensional means temperature is not function of. One dimensional means what? Temperature is only function of x and time. It's not function of y and z. ठीक है बेटा. In that case, I will write del upon del x k into del t upon del x plus qg is equal to rho cp into del t upon del t. That is what the equation is. No, tell me, am I right or wrong? When I'm talking one dimensional, then in this equation that term will be 0, only this term will be left behind, and since k is a function of temperature, that's why it will be inside. ठीक है बेटा. How will you write for now second case? Second, for one dimensional steady state heat conduction, steady heat conduction equation without heat source. Without heat source, how will you write the equation? Tell me. One dimensional steady state heat conduction without heat source. So without heat source means q is equal to 0. Steady state means del t upon del t is 0. Temperature will not vary with the time. No accumulation term is there when the steady state. One dimension means only the term is del upon del x. But k is a function of temperature because they have not given any information about the k. The del upon del x into k into del t upon del x is equal to 0. Is this clear? Now third, when one dimensional steady state qg equal to 0, k is constant, not function of temperature, then how the equation will be? And this equation can also write del become d because temperature only function of x, then d upon dx into k into dt upon dx. Can you write this? Del become d. Why? Because temperature is only function of x. And this equation become what? K is also constant, that become d2 t upon dx square equal to 0. But through uniform plane wall I should write here. Through a uniform plane wall. Uniform, yes or no? Through uniform, then only it's correct. Uniform plane wall. Uniform, yes or no? Bolo. Why uniform? Because area is constant, then only this equation we have written. What will happen if non-uniform is there? Anyone? Let's say if the condition is like this, these surfaces are insulated, no heat transfer in this direction. That's why I'm talking only temperature variation in x direction here. only temperature is going to vary in x. This is x direction here. Here temperature is T1 and here temperature is T2, the end of the rod, but area is going to vary. So how will you write the equation? Since we have to write the temperature variation in x direction only x direction, we should not write y. So I can go through this here, but here I should know area is not dx dy, area is only pi r square, normal direction of heat transfer, है कि नहीं? So let's say at any section area is function of x. So this is what the area na beta, this is what the area, and this area is a function of what? X. Here area function of y, area function of z. Are you getting a point? So basically what I want to discuss here, listen, you must know the restriction of your equations. So in general equation that I got here, listen carefully again, general equation that I got here is gradient square of t plus qg upon k is equal to 1 upon alpha into del t upon del t. My dear student, if this equation is written in this form, if qg equal to 0 and del t upon del t is also 0, means steady state, then this becomes del square t equal to 0, and that is called as Laplace equation. This is called as Laplace equation. If only qg equal to 0, then del square t is equal to 1 upon alpha into del t upon del t. This is called as Fourier's equation. Clear beta? Fourier's equation. But these equations has restrictions. Restriction is what? Only applicable for what? Cartesian coordinate, rectangular coordinate, and constant uniform area. K is not function of temperature. Clear beta? Then with these three restrictions you can use this equation without any hesitation. Clear? That equation you must remember. This will help you in writing the temperature distribution. Now listen, but as far as this may ask you for general, but in our syllabus only we have a heat transfer through conduction in x direction. X one dimensional heat conduction is there. So what I can do here, if one dimensional heat conduction is there, then out of this geometry, whatever I had taken here in this case, this is my system, and if in this system temperature is only function of x, then we should assume the differential element only in, tell me, if temperature is only going to vary with x direction, then we should assume the differential element only in x. In y and z we should take as a whole. So this was the y, z, this was x, and this is y. So what I will take in z and y as a whole, only I will take the differential element in x direction. This is what my, is this clear beta? बोलो, this is what dx. समझ में आया नहीं आया? I had considered the whole in z and whole in y. So listen, how separately I can write the balance, that's very important. Let's say this is what the slab is there. ठीक है, this is what x, this is what z, and this is what y. And here it's given temperature is only function of x. I'm talking about one dimensional, and this is variation in x only. So we should assume differential element, this is what x axis. So that seems to be like that. इसी को मैं only I'm talking about front view, then that should be seems to be like this. I'm not going to show the rest part below before behind this. Only this is what x and this is what y. Okay, my dear student, listen. So I should assume a small differential element. Let's say it's x equal to 0 here. So at x distance, I just assume a small differential element in x direction here. This is what a small differential element, and this is small differential element of thickness what dx. Clear? Dx is there, but actually everything is going to happen at the same that I have shown you in this case. This is what differential element at distance x from the this left face, and left face clear beta bolo. And I have to find out temperature distribution in this case, how the temperature is going to vary with x, that I had to find out. So then in that element we should apply the energy balance. Listen, then what do I add? Q dot at x, q dot at x plus dx. ये तो होगा, because no heat transfer in other direction, only heat transfer in x direction here. Temperature is only function of x and time. ठीक, so I will not bother about qy and qz. Then if I apply energy balance, E dot in minus E dot out plus E dot generation is equal to E dot stored accumulation. E in is q dot x, E dot out is q dot x plus dx. E generation is qg into volume. Volume is what? Because area is uniform. यहाँ area मान ली कितना बेटा A. This area, now this into this area is uniform. qg into A into what? What is the volume of this element? इसका वॉल्यूम कितना होगा बेटा? ये तो एरिया वही रहेगा सेम. एरिया इंटू डी एक्स इज वॉल्यूम. एरिया इंटू डी एक्स इज द वॉल्यूम. यस नो? And if it is qg, if the heat generation is given per mass, then density should multiply. Is equal to stored energy is what? Rho Cp into volume mCp, area into dx into del T upon del T. This is what accumulation term. Any problem? Now the same equation you can also solve by dividing the whole equation by dx. ऐसा भी कर सकते हो आप. It's all up to you. Otherwise, you can write the qx plus dx is, since also the two method is there. Since qx plus dx is nothing, it's what? Q dot x plus del qx upon del x into dx. Then qx minus this is what? Minus del qx upon del x into dx plus qg into area into dx rho cp a dx into del T upon del T. ठीक है बेटा? So this is what the general that you must know. How can I write this equation? Since from Fourier's law, what is q dot x equal to minus k into a area at x, qx है तो area at x into dt upon dx. And here since area is uniform, if it is non-uniform, then what should I write? I should, this ax should not be outside the differentiation. Only difference is minus of del upon del x into minus k into ax into dt upon dx into dx plus qg into a into dx is equal to rho cp, and this qg, this area should be also at x. Rho cp into a into dx into del T upon del T. ठीक है बेटा? Let's say I'm talking about steady state. For steady state 0. For steady state no heat source, qg 0, no source, my dear student. Then the resulting equation is here del upon del x into k into a as a function of x into dt upon dx is equal to 0. This equation has any restriction for area and thermal conductivity, and they'll become d. Why? Because it's only function of x here. Then d upon dx into k into area as a function of x into dt upon dx. In this equation, is there any restriction for area and conductivity? Area, no, area can also be function of x, then I can write here k can also be function of x, then I can, it's a inside differentiation, yes or no? So this is the equation for one dimensional steady state without heat generation, yes or no? बोलो. If k is constant, then I can take it outside. If area is constant, then take it outside, then become d2t upon dx square. है कि नहीं? So this k and ax will be inside the differentiation of that as long as the k and area is a function of x. If they are constant, then we can take it outside and it becomes same as a d2t upon dx equal to 0. है कि नहीं? तो अगर स्टार्ट में ही दिया हुआ है कि स्टेडी स्टेट इज देयर, देन इसको यहीं जीरो कर दो. नो जनरेशन, इसको यहीं जीरो कर दो. द ओनली दिस टर्म इज देयर. इज दिस क्लियर बेटा? दैट विल मेक यू सिंपल कैलकुलेशन. So if you check this equation, let's say now if area is constant, not function of x, and k is also not function of temperature, then the resulting equation become what? d2t upon dx square equal to 0. And this is same equation as here. In this case, no heat source, no heat sink, then only x is there, then d2t upon dx square equal to 0. ये तो आ जाएगा. बताओ कोई प्रॉब्लम बेटा? Now, so this is what about general heat conduction equation. Now based on this we will solve some question. Please revise the derivation whatever I discussed here. ठीक है? दीपिका बेटा कोई प्रॉब्लम? Thank you so much.